All right, folks. We left the morning session with a couple of questions, and unfortunately, it seems like they're not available in the Q&A section anymore. It must be because we closed the session. Anyway, those two questions were about data formats and about specifically, I have a screenshot of them somewhere. Yeah, the first question was about, I have a VTK grid mesh tetrahedra. Can I change the format so that I can use the parallelization features? First question. The second question was very similar. Question from Julia. So there are ways to change the data format, but not an explicit functionality that would allow me to change the format directly from a VTK unstructured grid to another format. So let me elaborate on that. I have a demonstration here. I have a Paraview session all set up, which I'm going to share with you. And then we'll discuss that. Wait a second. I guess you can't see my screen yet, can you?
Yeah, we can see your whole desktop.
Oh, you can. You can see that blob of that blue blob of okay. Oh yeah, that's working.
Yeah, we can see the whole desktop.
Yeah. Okay. So
okay, now we can see just the window. Yeah.
Yeah. So there is a big blob of data, and we'll get to it. This is simulation data actually from Professor Lucio Meyer at University of Zurich. Okay, so it's an SPH simulation, a set of particles. So there's no grid structure. I guess everybody's clear with the concept. We can have gridded data, rectilinear, structured, unstructured, or we can have particle data where there's no grid at all. So there's actually a couple of ways I can implement the reading of particles data in Paraview. One of them is as a VTK unstructured grid. The other option is as a VTK polydata object. All right. So I've taken my Tipsy reader. Tipsy is the name of the format which the University of Zurich is using to store their particles, and I have implemented the reader for it. So if I look at the object loaded here, so first of all, I have, you can see here on the left side of my panel, a multi-block data set, and one of them is the gas particle. So if I click on gas, it shows a polygonal mesh with one cell and 30 million particles. So that's fine. It has three variables stored on those particles: the smoothing length, H smooth, the mass, and the rho, the density called rho. How can I convert this data set to a structured grid data set such that I would get this as a display? Okay, let me put back the gas. So you can see I'm here now in the middle of the blob of particles. If I make the blob of particles invisible, I only have here I have a regular grid. Of course, don't look at the quality of the interpolation. It's very rough quality. I've done this for demonstration purposes. Let me turn off the color on this. And let me show the wireframe. There. You can see that I've gone back to a gridded data. There. So there's actually two ways to do this particular conversion. One of them, which is specific to SPH data, here I find under the point interpolation menu, I find those SPH Data Set Interpolators. So what I have used here is the plain interpolator. And if I look at the graphical user interface for this plain interpolator, I can choose my density array. I choose the name of my mass array. I can choose, here I've left it unset, the size of the smoothing length variable. I give it a spatial step, and then I choose the kernel, the implementation kernel, which I wish to use. By default, I use the SPH Quintic kernel. So this would be, and setting up here at the bottom, let me find it, the resolution here of my grid, 256. My output is an array okay. Well, it's not an array. It's actually still a polygonal mesh, but made of 256 square cells. That number is quite characteristics. So this is one way, dedicated to SPH. If you do not have SPH particles, but you have normal classical particles, you can use another set of interpolator, which you find under the still under the category of point interpolation, called the point set interpolator, line, plane, volume, etc. So that's one part of the answer. Another part of the answer is I'm going to demonstrate that with another script. I am over here. I'm going to create for you a rectilinear grid. Just to set up the discussion here. All right. Let me convince you that this is a rectilinear grid. I have a particular setup here where I have 21,000 cells. It's a grid of dimensions 40 by 30 by 20. And very often, let me look at the variable. Well, the variable is x, very boring stuff. This is the x coordinate. But if I wanted to do a volume rendering of this particular data set, I just cannot. As you can see, the set of modes available, I can show it as points, as wireframe, but the volume rendering option is not available. And this is exactly because we have a data of type VTK rectilinear grid, and the volume rendering option requires a VTK image data. So the second part of the answer about conversion is to use a filter called Resample To Image. So by default, I'm going to use a grid of size 100 cube, and I'm going to use the input bounds. So there, this was pretty quick because the grid is pretty small. I now have a VTK image data of type image, and the volume option is now available. So I can do a volume rendering of the particular variable. So we will go further into volume rendering later on, but here I just want to show you that this semi-transparent rendering called volume rendering is available once we have converted the rectilinear grid of the programmable source to the resampled image. Now this filter has the particularity that it uses multi-threaded computation. So it's actually, even on your own desktop, this would be a very fast execution because it's capable of using all CPU cores. Now, there's actually a third part to the answer about conversion of unstructured data to a parallel aware unstructured set. And I'm going to further demonstrate that with MPI exec. So let me run 4 tasks of my Paraview server locally. Let me connect to it. Let me run a wavelet. I will now convert this to tetrahedra. So I've gone from an image data to an unstructured grid made of 40,000 cells, tetrahedra for the precision. And we have a filter called D3 over here. D3 is a distributed data load balancer. So there are 3 options to D3. What D3 is going to do is it's going to measure how many cells are owned by each processor, and then it's going to do an even load for each one by transferring cells, tetrahedra, from one processor to the next until the load is balanced. So of course, the options of moving those cells from one processor to the next there can be multiple options to that. One of them is assign cells uniquely, which means that a given cell will be owned by a single processor. The second option is to make a copy of a particular cell to another processor. And the third option is to divide the cell exactly at the physical processor boundary. And as you can see here, I have an option to set the minimum number of ghost levels. So I can set those levels to 2, for example. Let it process my data, and I now have, if I color this data by the process ID, I have 4 different colors. My grid has been evenly distributed among 4 processors. And I should be able to see the ghost type. There it is. And let me set that up. So the ghost type is not immediately visible here. I have to go look inside the domain. So I'm going to do this with a slice. And I hope I hope this does it. Let me see. Ghost. For the moment, I don't see any ghost cells. So, okay, I think I know what I need is to do some contours, just like that. I still don't see any ghosts. So you'll have to bear with me for a second. Okay, so this is not cooperating. I'll have to redo this and show it to you tomorrow. Anyway, the main message actually is that D3 will do a global partitioning of your data. So this would be, it's not an ideal solution, because if you have a data format which only processor 0 can read, you would still need a large memory space to load your full grid onto one processor before being able to distribute it into multiple servers. So not the ideal solution. Now, if you were to use an underlying API, such as, for example, HDF5, which lets us do array slicing, you could implement pretty easily a reader for a tetrahedral grid, where you could slice your array of coordinates, slice your array of tetrahedral connection to load data into multiple processors. I have done this for a simulation code that runs at CSCS using an hexahedral cell. So if you need to consult with me about an implementation like this, I would be glad to provide the details. All right, I will quit this for the moment and go back to my normal presentation. I need to set up a particular example here to do my demonstrations. I'm going to reload the set of particles I had earlier. And then I want to make a subset of it. There it is. This is a subsampled version of the data set with, okay, 1 every 1,000 particles. So it's pretty light. It's pretty light. As you can see, I now have only 26,000 particles. And I want to demonstrate another way we have in Paraview to analyze and to select the data. And this particular algorithm method is called the matrix plot. So if I instantiate a matrix plot view here on the right, and I make this particular data set available, I have here a diagonal of histograms for each of the variables. So my data set here, the polygonal mesh, has 3 variables. So I have a diagonal of 4 objects, 4 matrices if you want. The first one here at the top is the histogram of density. The second one is the histogram of variable phi. The third one is the histogram of the distribution of velocity magnitude. And then at the bottom here are the coordinates array. Well, it's pretty cryptic as it is for the moment, but let me explain some more. Along the x-axis here at the bottom, I have the density array, the phi array, and the velocity magnitude. And along the vertical axis, I have the same variables, which means that for any intersection of those two axes, I have here on the top of the screen a distribution function of one variable against the other. So let's take, for example, the velocity magnitude as a function of density. Density is the horizontal axis. Velocity magnitude is the vertical axis. I can see here that I have two large peaks, two large clusters of particles, one of them with high velocity, the other one here at the bottom with lower velocity. Well, it turns out I can select by clicking and dragging, I can select in this particular fashion here. Let me see. Here I am in, I am in browsing mode. By enabling rectangle selection, here, for example, I would select in red exactly the particles which have a velocity magnitude greater than 0.1 and a density. I've tried to match, to go along the axis here, a density in between 0.1 and 0.2. Now this selection criteria gets visualized in all the different view matrices here. So you can kind of get an idea of where your particles are and how do they match the selection criteria. Furthermore, if I click on my window here, I should have those variables selected. However, for some reason I don't see them. Let me redo it. I should have the same selection available here. I should have on the left side of my screen. Perhaps I forgot something. I forgot to do an extract selection. There we go. So that's not as useful as I wish because it's only 1,000 particles and they are very small here on my screen. All right, so I'm going to go back to my selection and then do something different. For example, I would like to look at density against phi. The density, the phi variables selection over here. If I want to select all variables that have a phi greater or equal to, it would be that. And I should have, again, there we go. Now it's working as I expected. Let me zoom over here. All right. Let me clear the selection. Here's my disk of particles. Let me show the variable phi. As we can see, at the center of the galaxy, the particles here, which are blue, they have a scalar field, a scalar value, which is pretty small. It's below, let's say, 0.3 here at the bottom, at the center of my galaxy. Maybe I can make those points a little bit bigger, not so big. Let me adjust. I'm looking here at the point Gaussian representation. There we go. So those particles at the center are colored blue because they have a low value of phi. If I go into my selection matrix here on the right side of the screen, and if I select those variables with a high value, there we go. There are those variables. So there are the variables outside of the center of the galaxy. And this is exactly what we had found out in a visual fashion. So this is one way of interacting with the data, analyzing the data, where we can look at those cross-reference, if you want, a variable field and do selection of one variable against the other. And then doing this, we find out different patterns in the data. For example, here in the density versus phi display, we find out that we have basically 3 clusters of particles, one of them with a low value of phi, one of them with a midway value of phi and the full range of density, and then the third cluster over here, this branch of data, would be a set of particles with very low density and very high phi. So I could, for example, try to highlight this particular data set by doing this. There we go. And now I suspect, there we go. I suspect that the selection finds out those two over here, those two sets of very small particles which have these particular characteristics. So those two sets are far away from the center of the galaxy, but still they have a particular characteristics. And if we look at this particular selection, look, for example, at the display over here of velocity magnitude against density. This is what we expected from the physical point of view. We have 2 clusters of particles, one of them with high velocity, one of them with low velocity, and those 2 isolated clusters of particles actually match the criteria that they have a low velocity magnitude and a low density. There. Now, that's the good part about this selection criteria. And I can, over here, copy my active selection. I can extract those particles and make them visible. Sorry about that. Okay. There we go here. They nearly disappear from my screen because they're too small and there's only 1,350 of them. Now from this selection, I can save them to disk for further analysis. But the thing I cannot do is save the script as a Python executable. I will demonstrate that to you. Extract.py, because what I would like to have, I would like, instead of having a list of IDs, particle IDs, which match that particular criteria, I would like to have an expression which says velocity is less than, velocity is less than a particular value and density is less than. So to do this, we have to go to the find data points, and here we can do density is less than 0.2. And then with the plus, we add a query and we say velocity magnitude is less than, I forgot what values we were looking at. I would say 100. There we go. And I now have another selection where I have created a multiple query based on different less than or greater than expressions. There we go. What I was telling you is that if you save the extract Python script, we end up with basically an empty script. I'd like to highlight, if I can, highlight the piece of interest. There's actually nothing to highlight. It hasn't worked properly. Yeah. This is the failure of Paraview version 5.8. It basically writes a Python script with a completely empty selection criteria. Okay, so you need to bear with me. Version 5.9 of Paraview will have that fixed. In the meantime, that particular script I have actually holds the recipe to do exactly this selection criteria which we wanted. And here's the example that I have done. We use the so-called Paraview programmable filter. And inside that programmable filter, we use NumPy selections. So in this particular example, I have declared data to be my density array, data 1 to be my velocity array, data 2 to be my phi array. And if you're familiar with NumPy, this would be an example of an expression. NumPy log of 10, because we're using density data, so it's better to look at the logarithmic of it. NumPy log of 10 greater than -7. This is one of the selection criteria. And the indices of the particles which match this criteria are given by the NumPy where command. And this is the key to do this particular selection. So I will repeat the example here, and you will understand what is going on. Here, I have used as a selection criteria all density point greater than 10 to the minus 7. In other words, log of 10 greater than minus 7. And then I do a subsampling by 1,000, every 1,000 objects. Let me run the script again. So the message is basically that at the current time, there's my full data set here. I have a problem seeing my data. Let's see. Ah, okay. Okay, here I am. I was saying that at the current time, it is not possible for Paraview to create the Python script that replicates a selection which you do using the matrix view. However, you can do this with a programmable filter. The programmable filter, which I have shown you, is exactly this for this particular example, where I select using NumPy, where I select data with a particular criteria. So this is log of 10 of data greater than 7. If I look at my my data range here, this row, you see that I have data going from 10 to the power minus 16 to 5 to 0.52. So those particles that have a density greater than 10 to the minus 5 are the particles we are interested about. They are the center of the galaxy. There. So what is the message? The message is that here you have to do a case-by-case selection, and you would have to program this particular programmable filter in Python. So the syntax of this programmable filter is VTK syntax, pure VTK Python API. However, it takes a bit of knowledge of the internal data structures of VTK to be able to make sense of it. So if you have such a selection to do, I would be here to help you set up the program. That's basically the message here. All right. So particles here, we can color them with density. Yeah, so density, and because we want to use log, here we have a button, use log scale there, and we make more sense of our data. I'm going to get a bit more, 10 times more particles just to make them show up on the screen. Here's the color map interface of Paraview. I have here a set of default color maps. Some of them come directly from Matplotlib. So for example, the Viridis color map, and then you have a whole set of other color map that you are free to experiment with. And then you can have also a set of preferred you can have a set of preferred color maps which you import in the following way. So you would import that from a JSON file or from an XML file. This is for color maps. Now, in this particular case, we have different RGB colors for a different set of scalar variables. Okay, this is a linear, basically a linear set of points. Let me go back to a more standard variable, a more standard color map here to give a bit more explanations about color map. We see three different points here. One of them is this midpoint over here, which I can move and drag around. And basically what this is, you can see the numerical value here. So I can also set that to a very precise numerical value and to a very precise color. So if I want this to be white, I can make it like that. There, this would be a pretty specific, pretty specific color. And then I have an opacity function. So in my particular case here, all particles have the same opacity or transparency. And it doesn't matter so much when we look at particles data. It makes a much bigger difference when we look at surfaces. So I'm going to make such a surface by using the point interpolation plane, choosing the density, the mass, here choosing none, here choosing a spatial step of 1. Okay. I need to turn off the plane display. Okay. There is a very rough, I guess I could use something a bit smaller. There's a very rough interpolation. That example is not working very well. I'm going to quit and reload my existing script. Just like that. To make a decent looking plane of data. Okay, there we go. All right, I have a plane of data, and my argument was about color map and opacity mapping. If I enable opacity mapping for surfaces, just like this, and if I change this color map, you can see that I make more and more data available. I'm going to turn off the axes for a moment, such that they don't obfuscate the view. There we go. So I have something pretty neat here. because I have a plane of data. There we go. But it's semi-transparent. If I make this fully opaque, I get the regular display of data. So this is now, this opacity mapping for surfaces is going to be now the next thing we need to do, volume rendering. In volume rendering, we're going to take planes which are perpendicular to the view direction, and we're going to make them semi-transparent. So let me demonstrate that. I'll take the usual wavelet. Perhaps we'll make it a bit more interesting with something a little bit bigger. Not so big that you cannot do it on your own laptop. Okay. There is a display of data. There we go. A volume of data of size 48 cube. This is my surface display. And if I now go to, well, one step back, I'll go to outline mode. I will choose a slice of data. Do this. And now enable the opacity just like that. What do I have here? I have a plane of data which is semi-transparent. All the variables, all the points in the grid which are below this particular threshold of 22 are made invisible. All right. Now, if I have a single plane cutting through the volume. Now let's imagine that I want a set of multiple planes all parallel to each other. I'm going to use here on the left side of my interface a certain offset, so 5 minus 5, and let's see how it looks. As you can see, I now have 3 planes cutting through the volume, and they all use that semi-transparent mapping. Okay. Now imagine that you do this with a very small offset between the planes, then you have basically volume rendering. So I will forget about the slice and switch to the volume rendering mode. And I have what I had told you here, a set of planes perpendicular to the viewpoint, which show a semi-transparent volume. Just for clarity, I need to use an outline of this volume to make it a bit clearer in 3D. However, if I switch to outline, I lose the volume. And if I go to volume, I lose the outline. So one trick is actually to put here to put here a pass away filter, which by default get drawn as an outline, and I make my volume visible again. So there is volume rendering. I can now play with the color map. If I want to show only the data that has low density, this is what I would do. There we go. If on the other hand, I want to show the high density data, I could do this. etc. Now, there are multiple parameters that I can play with. The first parameters are the colors and the opacity of those control points. And then there's a whole set of other options which are available here on the left side of my panel under the display properties. And I'm going to show you the effect of some of those options. The first one is the scalar opacity unit distance. As I make this very large, you'll see that I have something very blurry. This is because the sampling density in the volume, which is basically saying how many parallel planes do I have going through the volume, that sampling density is too low. As I make this value small enough, I get something that is much better. Something like this. There we go. Now, this option about the volume rendering mode, smart, GPU, or Osprey, can make quite a bit of difference. If it's smart, Paraview will automatically detect if there's a GPU available on your machine, and if so, it will use the GPU. So in fact, on my machine here, it makes no difference if I use GPU or smart. The last option is Osprey based. Osprey is a rendering library created by Intel, which is also very fast for volume rendering. And I will demonstrate that to you tomorrow in the ray tracing discussion. This means that we can actually do ray tracing and volume rendering on pitch day using the multi-core partition. So if you do not have an allocation on the GPU side, it doesn't matter, you can still do some very high quality rendering using Osprey. One option of interest is the shading option, and if you watch the display, as you can see, we get a picture that is a bit more interesting in terms of shading. This is because it does an approximation of the orientation of this semi-transparent volume. Now, of course, here, this might still appear pretty boring and not very useful for visualization. This is because we're using a very low density grid. There's one more option, which is the blending mode. And one interesting option is actually the isosurface option. Here we have an isosurface, which is computed directly on the GPU using the volume rendering code. So there is no geometry to this isosurface. This would be the equivalent of doing an ISO contour of this volume with the same scalar threshold. So if I set here 120 as a simple threshold to remember, there we go. This object is the geometric object for this particular isosurface, and I can show it. I can show that contour with a wireframe so that you convince yourself that this is a geometric object. Okay. I turn this off, and the wavelet object is the same ISO contour, but computed on the GPU using the volume rendering code. So basically, this is an alternate solution to implementing volume rendering, to implementing isosurfaces. The advantage of it is that there's no geometry created such that we don't consume memory on the CPU side. Now, there's one more thing I want you to notice here. As I interact with the volume here, you can see some subsample data. And this is basically Paraview saying, in interaction mode, I want to use a very low density of sampling planes through the volume. And when you let the mouse go, it goes back to a full resolution rendering. All right, so that's about volume rendering. And to convince you that we can get some pretty nice display of it, I'm going to show you a video which I have made with volume rendering. Let me get to it. Okay, so this particular video here I have made last year shows volume rendering running on PitchDane on the compute node of PitchDane using a big fluid dynamic solution. Now, what is important here is that we had a very large grid made of 10 billion points. So the volume rendering was done in parallel. And Paraview is very smart in that it's capable of doing a composition of the multiple volume rendered images. What we're looking at in this particular field, in this particular animation, is the temperature field in this animation. And what we've done is we've made different zones of the volume with a different temperature assigned to a different transparency and color. So we see both the cold temperature zone in blue, and here, as we turn off the opacity of the cold regions, we only see the high resolution, the high temperature data. Now, it takes a little bit of work to achieve a result like this. Most of this work is actually in the definition of the color map, as you can imagine. So it takes quite a bit of tuning of your color map. There, I think maybe I'll zoom in to the very end here to show you the effect. Okay, good. I think we have enough of this. So tuning the color map. Let me go back to this wavelet example. I should go to the composite mode of Paraview. Tuning the color map is about using different colors there it is. So there is here the beginning of my cold and hot temperature as I had in the movie. As you can see here, I've made the red, the hot region here. I have given the hot region a pretty high opacity, and all the rest of it is made transparent there. And then as I increase this particular zone here, I have now a surface with a certain thickness, you could say. And I'm free to manipulate this until I get the appropriate rendering. So this would be the hot region of space. If I wanted something in the cold region, I would, for example, here add a little bit of transparency to this low region of data. I repeat, this particular example has a very low resolution grid, so it's not so easy to make something interesting about it. So this is about volume rendering, and fortunately, as you save the Python script, which you have at the current instant of time, all those numerical values about the position in the diagram, the position of those control points for the colors and for the opacity, those positions are saved. I will show you the script that would be written. Script interestingly, oh yeah, I guess that's it. We have those opacity transfer points over here, and then we have the lookup table, and those lookup tables are basically made of one scalar value and then one RGB tuple, another scalar value and another RGB tuple. So this is how you would fine-tune those parameters by modifying the RGB coordinates of those lookup tables. Okay, that's for volume rendering. Let me go back to my Paraview screen. There it is. For volume rendering, we have actually at Cscs a third option, which is to use the Nvidia index plugin. Now, to use the Nvidia index plugin, you have to explicitly load the plugin at runtime. So under the tool menu here, we have to manage the plugins, and we have to enable the so-called PV Nvidia index plugin. So I can load it like this. I can also make it to load as a default every time I run Paraview. There. To be able to activate the Nvidia plugin, because here it doesn't show yet on the list of available mappers, I need to close the render view, get a new render view, and here's the volume rendering I had earlier. Let me show the bounding box. And I now have a new option called the Nvidia index plugin. Now, as you can see, the differences can be minimal, but then the Nvidia index plugin gives us quite a bit more options. One of those options, for example, is over here to use a particular region of interest. So by using that particular widget here, I can crop my representation. This actually, interestingly, does not seem to function at the moment. No, I'm sorry. This is because I'm using the wrong interface. Let me go back to volume. Okay, there. Sorry about the confusion. Using the regular volume rendering option, this one here, volume, we have a cropping box which we can adapt to our liking in this particular manner. Okay, there we go. On the other hand, using the Nvidia index renderer, we have the so-called region of interest. So it's unfortunate that the two, on the graphical user interface here, the two things are next to each other because, as you see, I made confusion and I used the wrong set of parameters here. I think this is supposed to disappear in version 5.9. There would be no more confusion about those graphical user interface controls. So using index, I can now crop my volume as desired. There we go. Here, going back to the full resolution. So that's the first option. Second option is to enable here a plane. It's kind of hard to see at the moment. If I say why, well, it's hard to see because we have very low transparency. So let me reset that over here and turn off my volume. There we go. So what I'm doing here now is using the volume renderer of index. I'm looking at different slices through the volume, and I can do that in every direction in this particular example. Then once I'm happy with the setup, this would be something that you would do, for example, to fine-tune your column map here using only the plane intersect, the plane visualization. There we go. Once you're happy with it, you switch to volume and you would get your volume rendered visualization. I have a question here from Julia. Saying, is it possible to use the volume, those features, assuming the volume rendering features on my own laptop? My laptop has no GPU. So the answer is, if your laptop does not have a GPU, you would use the normal volume render option and use the, over here, use the Osprey renderer. Okay, so this should work on all systems. If you have installed the pre-compiled Paraview executables, those executables should be should carry with them the Osprey library. So please try that particular option. Okay, the Nvidia renderer, as you would expect, is specific to the GPU, so it will only work on the GPU. And if you have some big data to volume render, this again would be the advantage of using the distributed client-server solution of Cscs. So in fact, since I'm talking about this, I will demonstrate that right now. I'll go back to see the question, however. There's another question. Can I run Paraview from the Cscs servers and do X forwarding to my laptop? And the answer is you should not use X forwarding to run Paraview. This would give you very poor performance. So I'm going to demonstrate that. We're going to close this completely here and run Paraview. And I will demonstrate how you would actually connect to CSCS. So under the connect button over here, you should have a set. If you follow the documentation we have on our user portal, you should have set up a particular server host. And that configuration is called at CSCS reverse connect date. If I double click on this, you get a particular host name for pitch date. Now here we have to use a specific number. It's up to you, but you can choose date 103, 101, 102. But what matters is that this name doesn't change. You give it your username. You give it the path to your SSH command if you're using Linux. If you're using Windows, you give it the path to your plink executable. And then there's a default script which I have created and which is available. Please follow our documentation on where to find that particular script. My advice is to make a copy of it to your personal space such that you can modify that particular script. So I have modified mine with some particular customizations. Then you select the number of nodes and the number of tasks you want for nodes. So I'm actually going to select 2 compute nodes with 1 task only per node. I'm going to select the version of Paraview I want. I'm going to select the standard, the debug queue. And I'm asking for an allocation of 29 minutes. So this takes a little bit of time, but what it does is it submits a job to pitch date with the following characteristics. If you can see my screen over here, the job was submitted with the following characteristics: 2 nodes, 1 tasks per node, 29 minutes, just like I said, partition debug, constraints GPU. And this, using the GPU, would be available independently of the fact that your own desktop has or has no GPU, okay? So that's important. This is how you would get access to the GPU. Now I am available here, I am connected. And once you get connected, Paraview checks if you want the Nvidia index plugin loaded on both sides of on the client side. Those are the local plugins. And on the remote side, this would be the pitch date plugin. So here I'm going to say, please load the Nvidia index plugin on the remote side. I will close this. And now I can do my visualization again. Load a wavelet, and I can do some bigger data because I'm on pitch date. So let's do a 512 cube data. There it is, RT data surface. There's my data. I can do volume rendering in parallel. If I do this, as you can tell, I'm removing the zones which have a low value of the scalar field. I make them completely transparent. And here I have my volume rendering. So here it's independent of the processor. We don't see which processor does the job. And recall that in that particular session, I'm connected to 2 compute nodes. So the volume was subdivided into 2 halves. Now, going to Nvidia, the same would happen. I would, actually, that's very good. There's one particular flag that needs to be turned on when we do volume rendering with the Nvidia plugin, and that flag is called disable IST. So I should have done this before launching the job. So please remember, I'm not going to do this at the moment because I would need to restart. So I'll cancel this and I'll go back to volume. So there, I'm running my volume rendering in parallel using 2 compute nodes. Just as I did earlier, I'm adding here this pass array filter just to get a bounding box around the volume. It helps to see my data a little bit clearer. Okay, there it is. I'll go back to the question here to see. So one person, Luis, was saying, I cannot see the NVIDIA index slices on the property bars. So this should be there by default. Let's look at it. See, the NVIDIA index regions is over here, and if you turn on enabled on the index slices, you should have those particular slices. So I'm not sure what is going on with your display. Oh, yeah, sorry about that. Yeah, however, I cannot demonstrate it here in parallel because I didn't make the switch. Okay, sorry about that. Back to the questions. Some people are asking me about having a copy of the Galaxy data set. I will provide that at the end of the session, yes. So this is for volume rendering. I'd like to look at yet another set of representations in Paraview. And one of them is the so-called linear integral convolution plugin. I'm going to quit this particular session of Paraview and restart it. I'm looking for an interesting data set because you're probably a bit tired of always looking at the same. Yeah, let's take this data set. I will load all variables. This is the data set. It's a cylinder. With a different set of variables. So the type of this data set is unstructured. And one of the variables we have here is the magnet is v, presumably the velocity of data of the grid points. And as you can see, the default display is looking at the magnitude to do the color mapping. We can of course select the X, Y, or Z component of velocity for each of those vector fields. Now, if I were to cut this particular data set like this, I could still visualize the vector field in this particular fashion, showing the velocity converted to colors, but I could also look at it in a new way with the surface leak plugin. So this by default is also available on PitchDate, and I need to get a new copy of the reader of the renderer. And now I have an option called Surface Leak. And what this gives us is a convolution of the vector field along the path of very small streamlines integrated forward and backward for all points in the data set. So this would be the surface leak representation. Now, I'm going to do two different display here. Make a second copy of the display. I'm going to link one camera with the other. And in this particular view, show velocity in the classic fashion, okay? On the right side here, you have velocity magnitude mapped to colors. And on the left side, you have a convolution of a noise function along the path of this velocity field. Now, if I go back to the right side here, I could also do the following. I need to load yet another plugin called, I forgot its name now. Well, yeah, we'll have to use this as well. But the first thing I want to do is some streamlines. So I could do streamlines along the plane. Here we have to be careful to set the x coordinate to 0. I'll make those longer. With more steps. And this doesn't seem quite enough, so oh, I see. Yeah, we have very small. We have a very small velocity field, so this is not quite the demonstration I had in mind. So here's something we can do. We can take the volume we can, okay, the difficulty with Streamlines is that we have to seed the position of the streamlines in the volume. Here we have a cylinder, so I have to do this in the following way. Streamline, stream tracer. There it is. So we are now in 3D, okay? What happens is that we have taken, along this particular line, we have taken, let me reduce this because it seems to be a bit too many, resolution 100. We have taken 100 streamlines, seed points, and we have calculated streamlines in 3D. Now those streamlines still don't look very good in 3D. So let me show you how we can make this a little bit better. The first thing we can do is put a tube around them. Okay. This tube, of course, we can change the radius, make this half as much. We can color it with a, angular velocity, for example, here. What we can do is remove the slice in this particular display and only make an outline of the volume. So I would have to do it like this. Extract surface, like this, and then clip that surface into, for example, this is one possible solution, okay? So now in 3D, we have more or less the view of those streamlines. But still, it gets kind of difficult to see. And tomorrow we're going to talk about ray tracing. This is a good opportunity to use ray tracing, and you'll see why. Let me turn off. I need to turn off one object, which I don't see here. And it's the clipping plane I need to turn off because it's in the way. Okay, well, I don't seem to be able to do that. And if I use shadows, I get something a little bit more realistic. In 3D, it helps a lot to see the position of those streamlines in the volume. Okay. However, really the clipping plane should have disappeared in this, and I don't like to see this because this is a bug in the view of the clipping plane. I'll turn off ray tracing. I'll turn off the plane. And I enable ray tracing again. Well, no, like that's unexpected. Anyway, the ray tracing with shadows, as you can see, helps a lot in seeing those lines in 3D. So those are different ways of looking at my vector field. We can clearly see here in 3D this recirculation zone on the top of the cylinder, which is shown here on the left side of the screen with those very nice vortices using the linear integral convolution. All right. Let's go back over here to the streamlines. And I should have one more option, which is the streamline view. And as you can see now, coming up to my screen, I have something which I need to tune because it's too small. The default values are too small for the moment. There we go. Here I have an animated display. This is very rough because I did not tune those parameters very well, but this would give us an animated display of the data in space. So I need to still reduce that a bit to make it more useful. There we go. So we are working here with a steady state solution, looking at the vector field, okay? If I add now my clipping region, this is what I would have. And it's actually hiding the interesting part. So that's not so useful. Let's see if I have some questions concerning the linear integral convolution. It seems like it's all right. What I'm showing you here on the left side of the screen, I'm going to delete this for the moment, is that you can apply the linear integral convolution also on a curved surface. Okay, so we have it here on the outside surface. Now, of course, because it's the convolution of a noise kernel, here at the very top of the cylinder, where the velocity is nearly zero, we have a display that's nearly zero. However, here on the internal cavity, we have something that is starting to look all right. If I were to look at my slice again, let me go back to surface. If I go in the Z direction for that slice, there it is. I am inside the volume, okay, and I can see the recirculation of my fluid. So this would be very useful here to turn on the auto apply option. As you can tell, I can now look through the whole volume of computation in an interactive fashion. There we go. Now, since we are showing an animated motion here of the data, let me introduce you the animation view of Paraview. This will let us script a particular animation to move object in space and in time. So here we have found out that we can move our plane let's say, here we have a chord, a Z elevation of 7. And if I move down to this zone, I have an elevation of 0, okay? I want to do a scripted animation of this plane to save this as a video on my disk. How would I do that? I need to animate the plane between 0 with an altitude, a Z coordinate between 0 and 7. Let me do this with the animation view. There we go. The animation view is this particular panel here, which lets us select the objects which are on my visualization pipeline and modify those parameters. So here's for the slice object, the slice offset value, and I'm going to look at the slice origin, and I'm going to origin of 2, so that's the Z coordinates, and I'm going to add this to my animation track. Now, if I double click on this panel, I can set the original value to be 0, the high value to be 7, and I can now animate in time. Well, I can animate that through the sequence. Let me reset that to 0 and then play. Okay, I only have 10 frames set up here. Number of frames is 10. I modify this to 100 frames, and I'm going to have a smooth animation. Okay. Now imagine I put back my tubes in the display. I can still animate the position of my slice in time. There we go. Now, there's a number of things to pay attention to. One of them is the mode. Here, the mode is the sequence mode. The other one is snap to time steps. So if you were dealing with time-dependent data, where instead of streamlines, you would compute path lines, that is the position of points in space and in time. This is what you would switch your sequence mode to snap to time step, and Paraview would automatically synchronize the time steps which your reader is able to produce with this animation sequence. So this is the first animation we have here. Let's position. Let's say we want to do something a little bit fancier. We want to start with this particular position, and then we want to zoom in at the same time we animate the position of this slicing plane. Here's what we would do. We would go back here to the menu of option, and we would select the camera, and we would say follow path, for example. Follow data is actually a very good one, and I will explain why. Follow data is going to keep the data centered on the screen. So I'm going to remove the tube to make this more effective. And oh, of course, I didn't set it up. So wait a second. I said camera follow data plus. And then here I said data source to follow. I want to follow the position of the slice. I say OK. Then I reset. And then I play. And what is happening? It seems like the slice is not moving anymore. It is, but Paraview is keeping it at the center of the screen. So if I put back my tube object, I go back to time step to 0. See what happens now. What happens is that Paraview animates the position of the camera to keep the object to follow the slice at the center of the screen. Okay, so this is just one of the many options we have with camera. We can say follow data, we can say follow a particular path, follow an orbit. Let's do this one as an example here. We'll add this. Let's see, first we're going to delete this particular camera and then add the camera orbit. And we will play our simulation. And there we are now automatically rotating around the scene. Now I didn't set that very properly. I could by setting exactly, oh, sorry about that. I could set up I want to stretch that particular display widget, but it's not letting me. Okay, I have the camera position, the camera focus, and the camera direction. If I were to set that up to 0, 0, 1, I would have an animation, as you see, that keeps what it should, keep the vertical axis up. But probably it got reset. Oh yeah, because the camera focus and the camera position is still not set up correctly. I'd like to, there we go, show you what the orbit means. It basically is a path, and the camera moves around this path looking at the object. So this again needs to be fine-tuned to do a proper visualization animation. But I guess you get the main idea. So camera animation, the orbit, the data, we can animate the camera location around a spline or around a linear path. And then for each, let's try another type of animation. For each of those objects in the scene, for example, if I were to take an isocone tool of that particular variable, yes, I could animate that value. So this would be here an animation between those values don't make sense because the range of the scalar field is between 0.08 and 0.18. So I'll do 0.08 and 0.18 there. And as I animate, oops, something is not animating. Okay. All right, sorry, I didn't click the plus button over here. So there, I'm now animating the threshold of that isosurface value. And what I did wrong is I had modified this by error. I'll reset it to the original value 0 to 7. There. As I play my animation, I'm now animating both the isosurface and the position of the slice. There. So basically we can play with this for days and days and do some pretty fancy animation. And this would be all I have to say about the animation view at the moment. Any particular question concerning vector field animation? So I have a very good question here. I have scalar data Vx, Vy, and Vz. How can I transfer that into a vector? All right, so the answer I'm going to type, the answer is very simple. Use the Python, I forgot what it's called now, the Python calculator tool. Python calculator is over here. Yes. All right, so let me answer this fully. Use the Python calculator. Calculator. Okay, that's the answer to the question. If you have 3 scalar fields, you can make a vector out of them using the Python calculator. There. Let me demonstrate that. Let me delete this. Delete. We're going to delete most of the things here, which we don't need. There we go. We have a volume of data. V was loaded as a vector field. But I can do several things with it. Using the calculator, I could, for example, select the x component of velocity and call it Vx. There. I'll do another one. Calculator. Select the y component of velocity, call it Vy. One more for the z component, which I would call Vz, and I select the z component of velocity. Okay. At this point in time, I have a data set with variable v, the original vector field, and I have Vx, Vy, Vz, each one of them stored separately as a scalar field. The question was, how do I make a vector of them? I get the Python calculator and I type the expression make underscore vector Vx, Vy, Vz. And I'm going to call it result, and you'll understand why later on. There we go. So I now have, as you can see, the original data, V, each scalar component and a new field called result, which is exactly the same as V, the original data. In fact, let me do the slice display. I'm going to slice again in the X direction. There we go. There's X. Let me do a normal display. So this is the original vector V, the magnitude. Here's the X component. We can also select the Vx scalar field, and we have the same data. This is normal. And we can also select the result field, which is my magnitude of velocity. So if I switch from result to V, I should have no differences. So here's magnitude of V and here's magnitude of result. No difference. Okay, so this Python calculator can do a lot of good things for us. Let me demonstrate another use of the calculator. I'm going to get a second copy of the calculator, and I'm going to calculate the difference between the original data V and the scalar field and the difference between the original data V and the new field, which I have called result. I'm going to call this the difference, and I'm going to say V minus result. And I'm going to display the difference, and I get 0. I get here completely, this is completely blue. It says the range is from 0 to 10 to the power minus 38. It means it's 0 everywhere. We can check over here. The difference has a range that is 0 everywhere. So indeed, I have calculated the difference between two things that are identical. The difference should be 0. Okay, the point is that I can here put any expression I want with respect to my scalars and vector fields. All right, so I'll invite you to look at the documentation page on the algorithms of Paraview, on the Python side of Paraview, and you'll see that you have a lot of algorithmic expressions which you can type into this calculator. Now the calculator, of course, has the limitation that this is a single line of expression. If you have a more complicated expression which you wish to compute, you would use the Python programmable filter. Okay, so this was a pretty good question to illustrate the Python calculator. Let's see, what else did I wish to show you? The selection display. Yeah, this we haven't seen yet. Okay, I will delete this and go back to my slides. So here I would like to highlight the regions of space where the magnitude of velocity is very high. So this basically would be those two regions of space over here. Let me go to my spreadsheet view as we've done in the past. here's the, we need to select the velocity magnitude, sort by intensity, and we'll select here the points on the nodes on the slice where the magnitude of velocity is greater than 20. We can see them. They're highlighted exactly here in purple. So that's exactly what we expected. But I wish to actually show the numerical value right there on the display. So this is where I use the selection display inspector. And I select variable v. And I have it now on my screen over here. Of course, it's all on top of each other. It's not the best selection I could have done to highlight. Let me do a different selection. I'm going to clear this selection and I'm going to show you a selection on the screen. So I'm going to select points on the surface. For example, those vertices here. Let me see. I didn't do my selection. Okay, so, I see one, yeah. Okay, here I have 3 nodes selected, and I'm showing the value of velocity at those 3 nodes. I can also show another variable. This would be pressure, etc., or velocity, etc. Or I can show the ID of that particular grid point. This, again, would be very useful if you are debugging your code, your output. You are seeing some strange numerical values, which you identify, first of all, by doing a selection on the scalar field. And once you know the numerical value that are of interest, you can get the ID, the IJK coordinates of your points on the grid. Then you go to your debugger, to your simulation code, and you can go inspect exactly those numerical values at the particular index. So this is the selection display inspector. Let me go, before we close, let me go back to the information, to the display here. We've looked at most of the interesting things. Statistics is the following display here, which shows us for each object the type of the grid, the number of cells, number of points, memory used by Paraview, and the spatial bounds. We also have temporal bounds, by the way, yeah, which can be of interest. All right. All right, I have a question here from Julia about connecting your client desktop Paraview to the remote server Paraview on PID's date. Now, our documentation indicates that you have to set up a particular PuTTY profile, and on the slides I had shown this morning, there was an early example of setting up the tunnel to PID's date. However, the documentation here is pretty long. I have made a dedicated PowerPoint just to answer that question. So I recommend that Julia and all the other Windows users over here listening to me, please send me an email and I will send you that documentation. In fact, you know what? I'm going to post that solution directly on the slide. It will be just a second. I need to find the file. Okay, what I have done is I have put on the repository in the slides folder, I have put a copy of the documentation which you need to set up the Paraview tunnel using PuTTY on your Windows desktop. So it will be there in a second. I just need to push this, git push origin master. Okay, now you can do a pull and that documentation file is there. All right, folks, this is 3:30. So I had promised to make it a short section this afternoon from 1:30 until, actually I might be over time already. I forgot if I said 3 o'clock or 3:30. Anyway, there was time dedicated for questions. We've had some questions. I'm going to remain online following the Q&A for as long as you have questions here for the next half hour. If you have particular topics of interest, please type it in the Q&A panel, and I will try to answer to all people at the same time. Otherwise, tomorrow we have appointment at 9 o'clock, I believe. Let me check. The discussion is at 9 o'clock, and we're going to do photorealistic rendering with Paraview. And to whet your appetite, I'm going to show you a video which I have done, a couple of videos actually, which I have done with ray tracing in Paraview. So the first one is this. All right. So the simulation is about a plunging jet with air entrainment, which means bubbles which are entrained by the fluid into this volume. And this is basically ray tracing, I would say ray tracing at its best using Paraview and the pitch-date compute nodes. What I'm showing here is a volume rendering. Well, yeah, you could say volume rendering, of course. Let me stop here for a moment. There we go. We have a grid of data, which is made of a geometric object with surface normals, showing all the contours of the air-water interface. So for example, here under my map, this would be a first bubble of air within this particular volume of water. And then using ray tracing and using reflections and refraction of light through the water volume, I am able to do this particular rendering of the air-water interface in that simulation. And then the rest of it, as you see, the outside background, the floor and the walls are just there to help put context into this 3D simulation. So this is done with ray tracing, and I will demonstrate how to do that tomorrow. From the very basic OpenGL rendering to do ambient light occlusion, to do refractions, reflections, different materials, metallic materials, wood, water, etc. Those are all the things we're going to cover tomorrow. All right, folks, I think I will stop the recording at this time, but I will remain online. If I can stop the recording.